the audience, we are mostly like storage people. So a few words about containers, about the history, how we came. It's not a long history, but a little bit, what is the motivation, how did we reach where we are today? So that's from this morning's run with Jeff. Beautiful, high-speed sightseeing at Carlsbridge, so nice. So the historic things first, a little bit. I need to step down here and so, Nigel, did I wait long enough?
Yeah.
Good. So, all right. So containers. What are containers? Containers are actually an isolation of processes in a system. The containers usually consist of a runtime. Usually we are using currently Docker. There are other runtimes like Rocket, runc. There's an orchestration that helps us schedule the containers that comprise an application across nodes in a cluster, bringing them up and down again, stuff like that. There are various orchestration systems. One of our choice has been Kubernetes. There is Mesos, Docker Swarm, and others. So our choice has been seems to have been good so far. So this is about the container paradigm. Everything runs in a container. There's this microservice paradigm where you should, while you can run multiple processes, something like systemd and stuff in a container, usually you should have one container per process, and these talk among each other with defined interfaces and stuff like that. So it abstracts away the actual operating system of the host. So each container application comes along with its own whatever it needs of the operating system's runtime. So you can have a Debian operating system based application running on a Red Hat based host, stuff like that. So it's quite convenient. And one thing is, when all this came into existence, there was this rule, or this what it was implemented like: containers are stateless. So you can bring up the container and it's like a disposable entity. You can throw it away. When you bring it up again, everything that the container has changed in its directory, in its runtime, is just lost. So stateless, ephemeral entities. At some point people realized that this is pretty limiting. So these applications, they actually want to store some stuff persistently somewhere. They want some of their data, their configuration, their web pages, stuff like that. They want that to be stored so that it is not lost when the container is brought down. Hey, okay, that means we need some kind of persistent storage. And now, at some point, these providers of these container orchestration systems, they realized it. They started to bring in like NFS, or they directly consumed some local disks, either from bare metal systems or in cloud, like Amazon disks, Google, GCE disks, whatever. They use them directly, but this is not very flexible. But Gluster provides a very flexible, persistent storage. It is robust, it's scale out, it's totally convenient, it's software defined. So at some point, some clever people started to think about bringing this into the container space as a provider of persistent storage for these containers. Before going further into that, a little bit this Kubernetes thing. As I said, as storage people, we are wondering, what is this? Yes, this is this orchestration system. I briefly mentioned it. One thing, so what strikes me most every time is like, so Kubernetes people are a little bit strange for me. They are calling programs or processes apps, not to be confused with like mobile device apps. They are calling their users developers. So this is the major point of confusion. If a Kubernetes or OpenShift person talks about developers, it's not the guys developing Kubernetes, it's their users. Because these are usually some kind of people developing web applications running in containers, or some DevOps people. So I always find this a little bit amusing. And now you hear people, especially from Red Hat, talking about OpenShift. So what's this thing with Kubernetes and OpenShift? You can think of OpenShift as a kind of distribution of Kubernetes, where Kubernetes is the raw technology, OpenShift is Kubernetes plus a little bit sugar on top, basically. You had some security, some convenience, stuff like that. Not entirely unlike a distribution of Linux relates to Linux kernel or Linux kernel plus core components, core utilities. If you put all the convenience around that, you get a Linux distribution. And because I'm of course biased, I didn't want to have that show up so much, I named Debian as an example, right? So this is a little bit the setting with Kubernetes. So you have a cluster of nodes, and this Kubernetes system makes sure you have an application. You can, it takes care of running the containers for your application wherever. Containers are grouped together in so-called pods, and so when you hear people speaking about pod, it's the smallest unit that you can deploy an application in. It's one or more containers that are always started and run together and brought down together. So when you need more, you can scale the application up. Like you need more web heads in your application, you can say, hey, no, I don't need 5, but 10. It will make sure it's distributed across the cluster, stuff like that. Quite convenient. All right, so that's about Kubernetes in just very brief words. Kubernetes at some point introduced concepts for persistent storage. So the main concept is the so-called persistent volume, PV, as people like to call it. Persistent volume is the Kubernetes way of presenting some form of back-end persistent storage for the applications. The applications can consume this. It is requested and then requested by and then bound to a so-called persistent volume claim, also called PVC. This is the handle for the user, for the application. In modern times, I will come back to that later. So not so long ago, I mean, all that stuff is not very old. The persistent volume stuff is like at most 2 years old, I guess. So roughly at the time when we started thinking about these things also, roughly 1 year ago, people were introducing something called dynamic provisioning of storage, where the user actually, so the administrator is providing a so-called storage class, SC, storage class, and the user then can request, I need a 5 gigabyte, 100 gigabyte, whatever volume, and it is automatically created. So I'll detail on this a little bit later, because this is where Gluster really shines. Okay, after this intro about what is Kubernetes in containers from 10 miles above, so what were the starting points? There was Kubernetes, there was a Gluster. So assume we have a Kubernetes cluster and some Gluster deployment somewhere outside. Of course, you can go and manually create everything. So manually, as an admin, create volumes. Maybe a lot of them. Pre-provision these volumes, and then you can manually create these persistent volume entities in Kubernetes for your users to consume them. This is how it all got started. Like everything manual, a lot of admin work required to make it really nice. But yeah, that was the starting point. So people were thinking, how can we improve that? So that was when this Hekedi software that we talked about yesterday was introduced. So just summarizing, it's a high-level volume management interface to Gluster. While it was originally started as a project looking towards OpenStack, it quickly got used by this use case for Kubernetes. Kubernetes has this a driver or mount plugin where you can enable your persistent volumes to mount certain storage things. And here we, for the creation and so on, we needed this, sorry, I'm muttering. So the Kubernetes environment is all about web and RESTful interfaces and stuff like that. So you wouldn't go and do CLI stuff. Gluster only had CLI. It didn't have any kind of RESTful interfaces. So we created this Hekedi thing. And it has the CLI, but the main point is the RESTful API and the hiding of all the nitty-gritty details of volume creation. So you give it a certain number of devices and nodes, it will create everything for you. You just say, hey, I need a 100 gigabyte volume, and if there is enough space, it will create it for you. And what we did also is this Hekedi, like if you do it on the CLI initially, you create a volume. You can tell the Hekedi CLI to create this description of a persistent volume for Kubernetes for you. So that was when it really started to get convenient. Right? You could use Hekedi CLI, volume, create a size 10 gigabyte, and then you also set a persistent volume file, give it a file name, and it creates that file. Then you only have to do kubectl create for that persistent volume, and the persistent volume exists. So you don't need to go and manually create all these YAML files describing the PVs. It's all created for you. It's still a manual process, but instead of using your editor or templates and a lot of involved steps, it's just one command, Hekedi, and one command for Kubernetes, and you're done. So a lot of added convenience at that point. Well, asking different people, you get different answers. I'd say this is when we started calling it container-ready storage. So it was not native. I will talk about what native means in the next slide, but it was kind of, this was becoming more ready for the container world, right? Creating these PVs was just a piece of cake now. But now, container native storage, or native container storage, was when Gluster was actually put into the container space. So remember, before that, Gluster was running outside. Now, we had previously containerized Gluster. There was just no convenient way yet to run it in the Kubernetes space. So now what happened is you have the Kubernetes cluster. And on a few nodes, you bring up Gluster node containers. So Gluster is running there. It is consuming some kind of storage that's available on the hosts. This can be local disks. This can be network disks attached in the cloud or by some SAN, whatever. We don't mind. We have these Gluster nodes on some of the Kubernetes hosts, and then everything is running in containers. So you don't need an extra hardware, you don't need an extra runtime environment for that. It's all in there. And when it really started to get cool was in late 2000 or autumn, late summer 2016, when this dynamic provisioning was added. So then admin intervention really went down. Like create this so-called storage class describing how Gluster could be, and Hekedi could be addressed. And afterwards, the admin doesn't need to bother anymore, right? He gives the users or developers the description of the name of the storage class, and then they can just reference in their persistent volume claim, which is the request for a new volume, say, hey, I want a 100 gigabyte volume according to this storage class, and what they get back is the volume. So this is super convenient. Upon this request, the Kubernetes mechanisms go there, look, oh, this storage class, good. Let's talk to our Gluster so-called Gloucester Provisioner, which is a component in Kubernetes that we've been developing, mostly Humble and a few others. So this thing interprets the request, goes to Hekedi, tells Hekedi, please create me this volume. Whenever Hekedi goes to Gluster, lets Gluster create the volume. Everything goes back, and then if it returns, this thing has been created. No additional admin intervention required for creating volumes after the storage class, and the Hekedi and Gluster things have been set up. Super convenient. So this is native. First of all, it's natively integrating with these primitives of Kubernetes, like dynamic provisioning, and also it's running inside the container. So for instance, it makes everything much more agnostic. Imagine, I mean, of course, with a separate Gluster cluster, on premises, no problem. You can have this extra thing. But in the cloud, you already have rented or paid for a number of hosts there. Why not run the storage inside these? That's fine. You can attach these network disks to these hosts easily, and you have the whole runtime. It's super convenient. And in theory, or to some extent in practice, you can also scale the storage out as you like. You can add more nodes as you add more Kubernetes nodes. No additional hardware needed. So it is all basically, some people like to call it hyper-converged infrastructure with containers and Gluster as storage for the container applications. So this is a little bit the steps, how we came here. So it's really important to understand, or to have this kind of point of view, that adding our Gluster as a container native storage abstracts away the raw backend storage in a similar way like the actual container runtime and orchestration systems abstract away the real runtime from the application. So the applications can run anywhere that Kubernetes can run. And Docker, right? It can run on premises, it can run in the cloud on Amazon, Google, Azure, whatever. But with storage, it was always special. So with storage, you had to do it differently when you're using Amazon disk, when you're using local disk, SAN, whatever, Google disk. It's every time it's different. Here, we abstract this out. Once you have attached these things, our software-defined storage system, Gluster, with the additional convenience layers we added, makes this basically the same everywhere. So it reduces, if you want to put it like that, it reduces the vendor lock-in for your applications. It makes it much more easy to switch from one cloud provider to another. It was much more difficult before due to the storage. With this added layer of convenience, we can see Gluster here as a convenience layer for consuming raw storage. This is really what it is. So, and that was a big win. I think all the other existing storage systems that are either consuming local storage of sorts, which is very special, or consuming some external storage appliance, or NFS server, or some, I know NetApp has a special adapter for consuming their solutions, but it's an external storage appliance. It's not running natively inside the container space, so obviously. So this is quite an achievement and quite differentiator. Right? I don't know that there's anything like that today, at least not in the Kubernetes and open source space. So this is important to remember. Before going into the actual things for the title, I'm going to summarize next the past, present, and future bits. But before going into this, let me give you a few pointers. So we have, these are the major components components of our ecosystem where we are developing as the developers of the container native storage pieces. So let's go in the middle. I have mentioned Hekedi yesterday as well. So this is the repository currently. It's sitting between Kubernetes components and Gluster, obviously. So the Kubernetes has a couple of components. There's the Kubernetes core, which has our Gluster volume plugin and Gluster driver or mount plugin. But there are more components. There are new components coming. There is the so-called external storage repository in the so-called Kubernetes incubator space, where we have been developing recently our own external drivers for new flavors. I'm going to talk about that soon. So a couple of components where we are contributing to the Kubernetes space. Then, of course, Gluster itself and new components of Gluster, the Gluster block and Gluster S3 or Gluster Swift components, which we're also making use of as of recently. And finally, but listed first, is our project that basically ties it all together, the so-called Gluster Kubernetes repository. It contains the artifacts and deployment tools for setting this up. So it contains a tool called gkdeploy. You can call it, and it sets, assuming you have a Kubernetes cluster setup, it deploys the whole thing, Gluster, Hekedi, everything for you. So these are the components, and the ones where I listed the repos is where Humble and team are basically the main developers. All other components, we are working with the teams, with the Kubernetes team. We are part of the Gluster team and stuff like that. So we understand ourselves much more a part of the Gluster community, but we are working tightly with the Kubernetes storage guys there. So that's the ecosystem where we are working. And of course, I didn't mention the OpenShift flavors also there. I'm going to mention a few things where we took advantage of infrastructures that OpenShift offers in the next few slides. Okay, so it's been quite a journey. That's me preparing the slides on the trip here in the bus from Nuremberg. So now for the past. So basically summarizing in a few milestones what I've described as a historic journey in the past few slides. So the past, very historic. We containerized Gluster at some point, made it able to run in containers. Mind you, this is not a microservice thing. This is, according to these standards, a bad container. It's a very special container, privileged. It runs multiple processes. It runs systemd. It uses the hosts /dev directory for accessing the devices. It uses the host network for several reasons. So it's special. But we consider our storage here as part of the Kubernetes infrastructure, so there's a good reason for being special. We're trying to reduce that, but okay. Main point, it got containerized at some point, rather early actually. We introduced Hekedi. Hekedi has the while described here mainly for Kubernetes, it is a general purpose thing, so you can use it without Kubernetes. It has a certain executor backends. Yesterday we had them briefly mentioned in the slides, so by default, if not running in Kubernetes, uses SSH to talk to the Gluster nodes. In Kubernetes there is a special mechanism, kubexec, so Heketi has some optimizations for running in Kubernetes. The mount plugin, the driver, was developed in Kubernetes itself, and the dynamic provisioner was added in late 2000, or finished in late 2016. And when we did that, basically Gluster was, I think, the first storage provider to really implement this dynamic provisioning. So that's quite cool. And as I mentioned, the one command deployment tool to set all the complicated things up. So you don't need to do anything. You just give it the number of the IPs or names of the hosts where you want to have your Gluster inside the Kubernetes cluster, and it will do everything from there on for you. So that was the past. The major steps over the, let's say, year from 2015 to 2016, end of 2016, basically until last year's summit in Berlin. So for the present, let me show you what we've achieved since last year, basically, until now. So what's in that suitcase? In no particular order, I mentioned OpenShift. So we had this external deployment tool. There is no real deployment or installation tool for Kubernetes that we could hook into, so we had the separate tool. Not like that for OpenShift. OpenShift has an Ansible-based advanced installer. So earlier this year, we implemented in that upstream, in the OpenShift origin upstream, and then also going into all the releases since then, the option to have this installer install also deploy the Gluster cluster and set up storage class for you and something like that. So it has now become a genuine part of the, an optional part, but genuine part of the OpenShift installation. There have been a few enhancements to the actual provisioner. We can choose the volume type, you can set volume options, and stuff like that from the request. Like in the storage class, it can be specified. So the Kubernetes admin and users have the freedom of choosing what kind of storage, etc. they want to have. Very important, mentioned yesterday also, I think, so day 2 maintenance operations have been brought to Heketi at least, so we can replace a broken disk after or it's broken, or when we just want to replace it by a newer, bigger one, we can replace a node. Stuff like that has been done. Stuff like this was pages long instructions for Gluster core. Heketi does it in one command in that storage, in that Kubernetes space. Very convenient. Memory consumption due to all the brick servers running was really high. In this scenario, I mean, the cloud scenario or the container scenario brings us to whole new scalability requirements. Usually there are hundreds and thousands of apps they want to have their storage. So we need to provide hundreds and thousands of volumes. This is a high demand that was actually not there in many use cases before for Gluster. So brick multiplexing was finalized and brought into the Gluster code and releases so that we could reduce the memory consumption. So this was one of the things where the tight collaboration with the Gluster team was really awesome. So this allowed us for hosting more volumes on a certain, like nodes equipped with a certain amount of memory, like tripled at least the amount of volumes you can host on the same memory system. Then we added something that was a really big development effort. We added so-called support for so-called proper RWO, read-write-once support. So volume types with exclusive access in Kubernetes, specifically meant for applications like metrics or logging, some database workloads. The shared access patterns of Gluster FS volumes were not really good for that. And what we did is, in Gluster, we created a new component called Gluster block that lets you export with iSCSI files sitting on a Gluster volume as a block device with iSCSI. This is then consumed, so we integrated all that stuff into a caddy, basically a big code drop, completely new mode in a caddy, leveraging this. This is then brought into the Kubernetes space and then mounted with iSCSI methods instead of GlusterFS methods. So this was basically, this required work in Gluster, new component, entirely new mode in Hikedi. We created this external provisioner for that in the Kubernetes incubator space. So a lot of work. This was just released 2 weeks ago or so into the products, and it's been just in the upstream a little bit before that. So very, very new. That is quite an achievement because it allowed us to run stuff like this Cassandra and Elasticsearch stuff on Gluster volumes. Before that, it was only possible actually to run it on local disks, ideally SSDs. And so we were able to qualify that. That's quite cool. So it works, it doesn't break. It's basically fast enough. We also added experimental S3 object access. In this sense, the applications, how did they get our storage? Usually they get just from the host of the Kubernetes cluster, they get bind-mounted some file space as a directory into their container, so they don't even notice. The actual programs don't even notice. But sometimes these applications want to consciously access storage. Usually they want to do it with some kind of object access methods. They don't want a Gluster mount or something. They want object access. So we added this. It is not a native object access in Gluster, as you guys probably know. It is a Gluster Swift sitting on top of a Gluster file volume, and then even a S3 plugin, because S3 is the thing that the guys want to use. So we did it. So it doesn't have the advantages of the much more lightweight access to storage that a native object interface has, where all the metadata stuff of a file system is not there. It is still there, but it's mainly we needed to provide the API. It's not a replacement for a genuine object storage like Ceph has, for instance. But we are already in the container space, and it was very natural to add this. So as an experimental feature, this has been also added just recently. So what does the future look like? It is a little misty. There are a lot of possibilities. So I'm just, for the sake of time, I'm going to be very quick, but there are a couple of things. There's a lot of ask from the user and customer community to support something like you have 2 data centers, and if one goes down, you want it still to be, everything should be running. Of course, that can't work, right? I mean, everybody knows that. Like, 2-node cluster doesn't work, 2 data center, it also doesn't work, but we can think, what can we do? So we are working on it, maybe with some kind of tiebreaker node somewhere, something we are going to work out. Geo-replication has to be integrated more natively into the clustering world so that we can replicate between 2 Kubernetes clusters. So it needs to be integrated so that it's not only the backend storage that is replicated, but basically also the PVs can be carried over so that we can have some disaster recovery plan here. Scalability, yes, number of volumes has been greatly improved, but it will not be sufficient. So there are higher demands. We need to work on that to even improve it further. Deployment enhancements will also be there, like security, added convenience for securing the access to the volumes with TLS certificates and stuff like that. Backup plannings, monitoring the actual Gluster volumes. Our special container, it's so special. Can we make it less special? Can we move it from pet to kettle so that Kubernetes can freely scale our storage appliance? I mean, this will be a really big thing because it also will require some stuff in Gluster to be changed. There is more stuff. So Hikedi itself, I mentioned the state yesterday, external state database. It's in state on top of Gluster. So we need to reduce that. One plan is to move it into GD2, but we need to do something about it before. So before that can be made productive. So there is stuff. We want to be able to go into the brownfield scenarios. There is already a Gluster, and then we need to, Gluster cluster, we need to take that into Kubernetes. We also want to be able to do that. So performance sometimes is a question of Hikedi, of Gluster. HKD itself has issues. I think we're going to hear about that later. If you have thousands of volumes or many, many hundreds and you delete a lot of them at the same time, it takes too long. Maybe it even takes very, very long. So it appears to have been hung or something like that. So there are issues. We need to fix them. Further integration with Gluster block, like resize and snapshot is not available there. The S3 thing is experimental now. We need to expand it. And finally, it's more into the integration with Kubernetes primitives, like volume expansion, for instance, was there in Gluster, it was there in HKD, and has just been added into the upstream of Kubernetes. So in the next releases, we'll have that. Like natively now, as of very recently, Kubernetes offers an interface for expanding the volume size. So our native snapshot support, Gluster has it. We need to integrate in HKD and in Kubernetes, which is just being discussing about, or it's almost finalized, how to do snapshot there. And then the other bigger topics, like the container environment is discussing about standardization for storage access and so on, like this container storage initiative, CSI. It's not like the crime scene things, right? And there's more stuff, like people are talking about these operator patterns. Is our deployment model good, or it should we more follow this paradigm of operator doing everything for us? So there are a lot of things we can think about, but it gets more and more misty. So maybe I should stop here, and maybe I'll have time for 1 or 2 questions. Either it's super clear, no questions, or everybody has fallen asleep. Either way, thanks.